So today, as I said, I'm a chemist, but I'm going to talk about the grid today because I think it's such an interesting topic that's really being talked about a lot in a way that I think wasn't talked about as much maybe a year ago and is really coming to the fore. And there's lots of policy and regulatory changes that are happening to make it quite an exciting time to invest in the grid and innovate and just yeah, it's an exciting topic. So at Zero Carbon, we're focused on investing in entrepreneurs that solve the biggest challenges of decarbonisation. So as you might be familiar with this chart already, if you're not, it's fantastic. It's from 2020, but it more or less applies. And we can see that about 73% of the 50 gigatons of emissions we have each year come from energy, so fossil fuel generated energy for industry, for home use, for transport, for all of those things. And really, in order to achieve decarbonisation, to achieve net zero, we kind of need to, electrify all of these processes that rely on fossil fuels and also use renewable energy to provide that electricity. And we're making good progress in some of these areas. So solar and wind are adding to the energy supply faster than any other new energy source in history. So you can see the beginning of this hockey stick deployment. You know, we're getting rapid deployment. They're the cheapest sources of energy, and it's only getting faster. So that's really positive. Electric car sales have increased 2,000 times. So that's 3 orders of magnitude since 2010. And again, we're just in the inflection point of this hockey stick deployment of electric cars. Heat pump deployment is a bit slower, but we know now that it will be the best way to heat our homes and to provide some lower temperature industrial heat using electricity and ultimately require less energy than the fossil fuels would have needed up to this point. So we're making good progress. And all of this electrification relies on the grid because it's the blood vessels, it's kind of the backbone of our whole energy system. So what is the grid? What does it consist of? Well, it consists of power plants generating the electricity. It consists of transmission lines that carry the electricity long distances. So they carry electricity at 400 kilovolts or above, and so you need a transformer to step up this voltage. And it's very high voltage because that's the most efficient way to transfer energy. And they transfer it using alternating current at about 50 hertz rather than direct current. So all that means is that the alternating current has a set frequency, and it needs to maintain that frequency of 50 hertz to maintain stability and ensure that there aren't blackouts. And again, AC is just a more efficient way to transfer electricity over long distances, and it's easier to step it up and down than direct current. So that's why our system relies on AC. And then you have the distribution system, so many more distribution systems and much more distribution lines overall to take high voltage electricity from the transmission system and distribute it to the end users. So that might be your home at 230 volts, but there are also industrial connections, data centers that might connect to higher voltage parts of the distribution system. So who's involved in this? Well, you have lots of different stakeholders. You have the transmission operators that have to balance supply and demand in real time at all times. You have distribution operators, and again, there are many more of them all over the country that ensure that delivery to the end customers. You have the solution providers, so they provide the hardware and the software to these transmission owners and operators. And then very important in the grid are the regulators. So because it's an important service, it's a regulated market, which can make it slightly more difficult to operate in than a typical kind of open market. And it's these regulators that set the remuneration frameworks for the system operators and how they can how can they charge consumers and then get remunerated for the services that they provide. And really, this is one of the challenges of the grid, is that these regulation systems really favour security and reliability of the grid, which is obviously important, but can sometimes make it more difficult for them to innovate and introduce new technologies. So as I mentioned, it's the backbone of the energy transition, but it's under strain. That the energy transition and this move towards renewable energy is kind of a different system, and it's struggling to cope. So the first challenge is just increasing demand. So actually in the US and in Europe, energy demand has kind of plateaued, or electricity demand has plateaued or even gone down in the US and Europe because of increasing efficiency of our appliances. But at the moment, it's just starting to go up again. As we add the electrification of transport to the system, as we add new data center demand because of AI, these are all adding loads to the grid. And so in order to accommodate this in developed economies and also the growth in developing economies, the IEA estimate that we need to double the length of transmission and distribution lines by 2050 in order to meet our net zero goals. So that's a lot more lines and a lot more money that will be going into this area. So I think, investors are often reticent to invest in these regulated markets, but it's a huge opportunity because we will need so much more investment in these poles and wires, etc. The second challenge is the increasing complexity of the grid. And so this is the complexity that's introduced by adding renewables. So whereas before we had kind of these highly centralized fossil-based generation that was dispatchable, so you could ramp up and down on demand really easily, and all the energy flowed in one direction from the power plants to the end consumers, and it was quite straightforward. Whereas now you essentially have renewables. They're much more distributed. They might be in places where it's windy or sunny and not necessarily close to load centers where you can just put your power plant there. And so this has some impact. The fact that it's geography dependent, so both in the UK and also in Germany, you have lots of offshore wind in the north and large load centers in the south. And so you end up with congestion where the lines that connect the high renewables to the load centers are really congested. And they can't carry all of that energy. So what that means is that you have to turn off or curtail the wind energy in the north and then turn up fossil-based generation in the south in order to meet the demand. So it's not only more expensive because you have to pay them to curtail the energy, but it's also not as green because you have to use fossil to compensate for the fact that you have this congestion. And then, of course, you have the added complexity of having more distributed energy resources, so EVs, solar, and now the grid not only becomes, has more generators, but it's bidirectional, so that digitalization is a challenge as well. And finally, inertia. So this is really important for the stability of the grid. So because the grid has to maintain that frequency, and actually fossil-based resources that rely on turbines, the turbines are spinning and producing the frequency of the grid. And if one of those turbines fails, or if one of the power generation fails, that turbine keeps spinning. It maintains its inertia, which means that the frequency is maintained because it keeps spinning. And so they have time, it buys time for the grid to turn on some more generation elsewhere if you have that problem. And renewables don't have inertia, so that can introduce stability challenges as well to the grid. The third challenge is safety and security. I won't focus on this too much, but more extreme weather compromises the safety of the grid, and also the fact that the grid is aging and maybe sagging. Sagging wires can lead to more safety challenges and fires and things like that. So it's all interrelated. And then increased digitalization also increases the cybersecurity threat. So this is a challenge for the grid. And finally, this kind of bucket of non-technical challenges that are a very big problem for the grid. So firstly, permitting timelines. So permitting and building overhead transmission can take up to 10 years or over 10 years. Same with underground transmission and subsea cables. And another big problem to do with permitting is these interconnection timelines. So what you have here on the bottom right is a graph of installed capacity on the US grid in 2010, so about a terawatt of installed power. And in the queue, some solar and wind projects that want to be connected. And in 2023, you now have more solar and wind installed, so you have about 1.2 terawatts on the grid. But you have twice as much as that. These are projects that have been approved that are waiting to be permitted, waiting to have their connections permitted so they can add that load to the grid. Now, the fact that it's so big is also a function of how dysfunctional it is, because many of these won't get built and they're kind of hedging by being in the permitting queue. But this is a big problem and something that's changing at the moment in order to accelerate deployment of grid technologies. So that's to set the scene. So how can hardware technologies contribute? And of course, there are also software technologies and lots of different hardware technologies. I'm just going to focus on 3 examples today in the interests of time, but there are many others that are also interesting to look at. And so the EU refers to what's called innovative grid technologies. You might also see the terminology grid enhancing technologies, or GETS. There's a lot of acronyms in grid technologies that you kind of have to get used to or have a glossary to refer to. But these innovative grid technologies are essentially technologies that can increase the power carrying capacity of the grid without having to build new transmission lines and new transmission towers, which can get around some of the issues with permitting, because people don't like having a transmission line in their backyard. So if you can use these innovative grid technologies to increase the capacity without having to build new transmission lines, then that can solve some of the issues with permitting. So I'm going to start with reconductoring to increase capacity. So reconductoring is the process of replacing the traditional conductors that we use between the towers with advanced conductors made of new materials that have higher current carrying capacity. So traditional conductors are these aluminium ones. So you have an aluminium that is lightweight and has high conductivity, and then steel in the middle that doesn't have as high conductivity but has high strength to maintain the wires between the towers. And these advanced conductors often have a carbon composite core, so it's lightweight and has better conductivity than the steel or the aluminium. So you can essentially carry twice as much capacity along the same line. Now they're more expensive, like meter by meter, than the traditional conductors, but the overall project is cheaper than building new transmission. You can use existing rights of way, you use the same towers. So that's advanced conductors, and then superconductors are even a supercharged version of that, where at low temperatures, when you go below a critical temperature, they essentially have no resistance. So you can carry huge amounts of power along the same line. But the problem is that they need to be at very cold temperatures. So you need to keep them, you need to have insulation, and you need to keep them at cryogenic temperatures. So that is a challenge that needs to be overcome for these types of conductors. But it's one that, as technology investors, is an attractive proposition, because if we can provide this investment and bring down the costs, then we can make them more widely available, is the idea. And we can see this on the right hand side here. You have a picture of a project in action where they've used advanced conductors. So on the left hand side, they have the carbon composite conductors versus traditional conductors, and you can see they're higher strength, they have lower sag, so they're safer. And if you have lower sag, and you're building new transmission, you can essentially space the poles further apart. So lots of interesting, like co-benefits of using these advanced conductors as well. And here are a bunch of startups that are working on advanced conductors and superconductors. So that is reconductoring. The next thing I want to look at is storage on the grid. So storage as a transmission asset. Storage as a transmission asset is basically storage, and you could say, oh, it's used for generation, it's used for transmission. There are lots of different value propositions for storage on the grid, but ultimately it can play multiple roles, and either way it's kind of contributing to the energy transition and enabling more renewables deployment on the grid. So this, I love this. This is from the New York Times, and you can see the impact that lithium-ion batteries are having on the grid, in just the last 3 years. So in April 2021, you already had a lot of power on the Californian grid, the solar power. But there was this problem that the peak of solar output did not match the peak of consumer demand. But now by April 2024, they've got many more lithium-ion batteries installed. That means they can charge using this solar power and really meet that peak demand. So you can see how much less gas they've needed in 2024 to meet that peak demand. And this is only going to increase. So that's quite cool. Batteries on the grid also have other applications. So load shifting was the one we just looked at, shifting that load into the evening. They also do frequency regulation. So they don't have, so whereas renewables and batteries don't have inertia in the same way that these rotating turbines from fossil fuels have, what they do have, so they can't buy the time to turn generation online. What batteries do have is the ability to respond very quickly. So instead of having inertia, they can essentially just boost the energy on the grid really quickly and provide sort of synthetic inertia to the grid and provide that frequency response that is so valuable. But also they can reduce congestion and curtailment by, instead of wasting all the wind power that's in the north of the UK or the north of Germany, or even in the US, you can see how congestion costs have increased on all major grids in the US as renewables deployment has increased. By storing some of that renewable energy, you can reduce the amount of curtailment and reduce congestion. And they call it deferring transmission and distribution. Like ultimately, you probably need more capacity or more reconductoring along a single line, but installing storage can act as a transmission asset in the meantime. And this is all kind of thanks to the cost declines of lithium iron phosphate batteries on the grid. But that there are some applications for which lithium iron phosphate kind of isn't quite good enough, because as you need longer discharge durations, maybe overnight, lithium ion batteries become a bit too expensive. And so these are sort of what we would call long duration energy storage. I'm defining long duration here as 12 hours plus, basically anything that lithium ion can't really do. And so this is for overnight like energy storage applications, maybe storing all of the excess solar during the day and being able to last all the way till the next morning. But also it needs for even longer duration, so multi-day low renewables events, which I believe in Germany is called Dunkelflaute. I don't know if that's how you pronounce it, but it's a term used in the energy world to basically describe those days where you have low wind and low solar. And we need cheap ways to store that electricity for those longer duration periods that you can't use lithium ion batteries for. So some options here are to use sodium ion batteries. So sodium ion batteries have the same form factor essentially as lithium ion batteries, but sodium is much cheaper and much more abundant. So the idea is that they could become much cheaper than lithium ion batteries. Or you kind of decouple the power from the energy, which you can do using things like redox flow batteries or thermal storage or some other technologies like compressed air energy storage, liquid air energy storage, and pumped hydro. Again, I'm very happy to talk more about long duration energy storage. I've just kind of touched on it here and tried to highlight some of the European, because we invest in Europe, tried to mainly highlight some of the European startups. There are more startups globally, but I've tried to highlight some of the exciting European ones in each of these areas here. And finally, I want to talk about some of the challenges facing distribution grids and how we can kind of manage new loads and the power quality on distribution grids. So this image here on the right actually is transmission data rather than distribution data, but bear with me. So this is the electricity. This is a kind of classic example, at least in the UK, but I'm sure it applies elsewhere as well, of what happens to electricity demand when it's the World Cup final. So it was the Euros final on Sunday, and we were sad to lose in the UK, but well done Spain. They probably deserved it on balance. And this is kind of shows how the peaks in electricity demand in the UK during one of these matches. So you can see kickoff starts and demand goes down. People just have their TVs on and they're just watching. and watching TV, and you can see at half time there's a massive peak. These lines are for two different matches. There's a massive peak as people leave, they turn the lights on in the kitchen, they turn the kettle on, they open the fridge to get a beer, and even all these individual actions lead to a massive collective surge on the energy grid that the transmission system has to manage. And again, you can see at full time there's another peak. And I think this blue one was England versus Italy, where it went to extra time, so you have some other peaks as well. So this is on the transmission grid, which can kind of be balanced out over the whole country, and they can predict it in advance, and they have to manage these loads. But this is much more challenging to do on a distribution grid. And why is this example relevant? Well, basically, because of the new loads we're adding to the distribution grid, it becomes much more challenging to manage them. We have aging infrastructure with quite limited monitoring capabilities to date, and limited flexibility based on current technologies. And by adding, it's particularly EV loads, they're quite a big load to add to a house. And if you imagine the collective behavior of everyone coming home from work and plugging in their EV when they get home, you can see how on one street, if many people plug in their EVs at the same time, it could really affect the stability of the grid, the distribution grid in that area. And so what are some technologies to deal with this? Well, advanced transformers can help in this space. So they're an interesting application. So traditional transformers basically use magnetic steel cores to ramp the voltage up and down, and they're installed at substations. You can have them at transmission level, at distribution level, and they're basically passive machines, and they don't have much control. You're just increasing the voltage. So if you have any kind of instabilities in your voltage, in your voltage, then that will be translated into the high voltage or the low voltage. And so advanced transformers solve some of these problems by using power electronics instead of these passive components. So at the very least, they have much better monitoring and analytics because they can analyze the voltage coming in and out, and they can basically actively control the power quality, the voltage compensation, and manage these bi-directional power flows that are only going to increase as you have EVs pulling from the grid, contributing to the grid, and rooftop solar, etc., etc. So these are some quite exciting technologies, and there are a few companies in this space. INA is actually one of our portfolio companies. But there are others too in the US, in Singapore. So an interesting and exciting space that can enable much more distributed energy resources on the grid. And just a final nod to policymakers, because people often talk about how the regulatory environment for grid technologies is really challenging. But I think that's changing. There have been new rules announced by FERC, so the Federal Electricity Regulatory Commission. Oh, there we go. Energy Regulatory Commission in the US is introduced new rules. In the UK as well, we've introduced new rules to increase the speed with which renewables are connected to the grid. So regulators and policymakers are really recognizing that this is a big issue and trying to accelerate the energy transition. So yeah, just to reiterate, why this is such a good time. We need to double the length of transmission distribution lines, which will help us avoid many more emissions in 2050 if we're able to do this. We can achieve cost savings overall by reducing congestion and all the overbuild of transmission that we need. And the regulatory environment is changing to favour all these decisions. And finally, this is just a market map that I made. This is on our website with a bunch of other technologies that I haven't had a chance to all go into, but feel free to check that out if you're interested in looking at any more of these companies. And so this is just a picture of some of the rest of our team and lots of our amazing founders that we love. And yeah, that's it from me. Please, would love to hear your thoughts and questions, and get in touch if you want to chat.
Thank you so much, Chloe. Super interesting. And I'm definitely sure there are some questions. So I would say, whoever has a question, feel free to put them in the comments, or also just raise your hand. Otherwise, I will also read the questions out of the chat. I think there is actually already one from Mike. Do you have a breakdown regarding the cost of kilowatts per hour, and especially how much the grid contributes to that? So at a cost of 30 cents per kilowatt hour, how much of that price can be attributed to transmission, generation, and storage?
Yeah.
Many thanks.
So I don't have that data here, but that's a really good question, and it differs a lot by country. I tell you where they do have that data. I can see if I can try and find it. There's the IEA did a big report either earlier this year or last year on the grid the transition of the grid, and there's lots of interesting data in there about what proportion of your bill that you get from retailers is due to transmission and distribution costs. Yeah, I don't have it here, but it's in there, and I'll see if I can find it.
Yeah, perhaps. I mean, perhaps we can also, whenever I later share the presentation or something, we can add that info also for you, Mike.
Yeah.
I mean, because you also now said this, like, how much is actually the that was a question on my side, like the local system, or how much is a local topic versus a global topic. So if you build a great transformer, can you apply that in every grid worldwide? Because it of course also impacts your investing.
Yeah, I think yes, like every grid worldwide will need things like transformers. So broadly speaking, they can apply in lots of different places. With something like storage, they might be used slightly differently. Like in some emerging economies, you're much more likely to see the emergence of microgrids where they don't necessarily have they don't yet have a very developed kind of macro grid that covers the whole country, but they have, you know, lots of potential for solar, and solar is really cheap. So they build these microgrids that consist of solar and batteries, but it's still kind of the same batteries that can be used. They're just implemented in a slightly different way.
Are there any other questions at the moment? Everything so overwhelmingly clear. There is one. What is your take on the profitability of using second life batteries for stationary storage applications, BSS? From a VC perspective, what problem of the energy storage value chain seems lucrative to found a venture? Okay, so let's go with the first question. These are two different ones. What is your take on the? Sorry, go ahead.
Yeah, what's my take on second life batteries? Are they a good option? I mean, so in principle, they would be a good option. I think you need to do quite a careful techno-economic analysis, and I'm sure that people have done this. I don't have a paper that springs to mind, but there are real challenges around, even though in theory it's much cheaper, ensuring the quality control of all those batteries. And especially if the lifetime of car batteries actually ends up being much longer than we think it will. Will there be enough second life batteries? You have to ensure that they don't need to have the same, but you need to assess the degradation profile, you know, how much lifetime it's expected to have going forward so that you can issue a warranty and things like that. So I think it divides opinion. You know, it's in principle a really good solution and good for, you know, the circular economy and things like that. But it might be that because lithium LFP batteries are getting so much cheaper now, you have to factor in all that additional conditioning and testing that you need to do before you build your second life battery, and compare it to the fact that batteries are actually getting much, much cheaper. So in principle, I think it's a great idea. I haven't done the techno-economic analysis to know whether it's super investable at this stage or not.
Or if it's then the
We'll look
topic
at it.
of battery recycling.
Yeah. Battery recycling, yeah, either directly for reuse a second life or yeah, extracting the materials and all the different ways you can recycle those as well.
Yeah. And the second question was, from a VC perspective, what problem of the energy storage value chain seems lucrative to fund a venture, to fund, I guess, to fund, or and for a founder to start a venture?
Yeah, sorry, just to interrupt. It was to found. So yeah, but basically from the VC perspective, to fund, so both apply. Yeah. And thanks
Yeah,
for your
that's cool.
response, Chloe, regarding the second life batteries. So I've done like, I mean, you're absolutely right. There's basically a threat from a decreasing price of new LFP batteries. And I've done kind of a techno-economic analysis on this during my master's thesis. But I believe the field is constantly evolving. And I was just wondering, as a VC, do you see any startups in this space?
Yeah.
And what the investment landscape looks like from that perspective?
Yeah, I have seen a few startups in that space. We haven't actually made an investment in those in that space, but I'd be interested to see your techno-economic analysis because I imagine the outcome does depend a lot on what you expect the price of a new
Right.
battery to be.
To be in the future. Yeah.
Yeah, yeah.
And
I'd be
considering
really
that there's no other breakthrough in storage technology like you were talking about earlier.
Yeah, but I think there's lots of space in storage to have things that are optimized for different applications. Like things like lithium-ion batteries are so good for the opportunity of arbitrage, like buying really cheap electricity when there's lots of solar and then selling it when it's really expensive. Because they have such a high round trip efficiency, you don't lose much of the energy on charging and discharging. That
Right.
lithium-ion batteries are really good for that. But then some of the other ones like redox flow batteries that have lower round trip efficiency won't
Right.
work as well for arbitrage, but are good for longer duration where you really need that cheap energy component.
Okay.
And then your other question was where in the value chain,
Yes.
what do you have in mind when you ask that question?
So, I mean, there's multiple problems to be solved as far as storage goes. I mean, one is arbitrage or frequency control, peak shaving, various applications that basically BESS can be used for, right? So, from a, let's say, investment scalability perspective, what do you see as a promising use case?
I think we kind of need things for all of these issues. So frequency regulation, I think that problem is solved by lithium-ion batteries to a certain extent. And actually, I've read pieces that say, that market is already saturated. So
Right.
by batteries, so that's kind of, I guess, problem solved. So that's quite good in a way. The real challenge becomes the longer duration, I think. So when you're getting above 12 hours, it's difficult. As I mentioned, there are lots of different technologies. So there's redox flow, there's thermal, there's loads of other technologies that are quite similar in terms of their value proposition. But currently the markets don't incentivize like longer duration storage. So maybe we don't need it yet. There isn't a need for it yet. But as renewables penetration increases, we will need some storage for those days where where there are multiple days with low wind and low sun. But those markets haven't emerged yet, so it's not clear how those technologies will be remunerated.
Sure.
And so it's difficult to pick a winner, and lithium-ion batteries are also getting so much cheaper that they're kind of eating up like big chunks of the market that they might play in terms of wholesale markets and things like that. So we ask this question a lot, and I feel reticence from a lot of investors to invest in these medium duration storage because lithium-ion batteries are getting so cheap.
Right. So there's a lot of uncertainty in the next 5 years as well, right? Where the price goes, and it's hard to, really bet for sure in one direction, I would say.
Yeah.
I agree. Yeah.
But we should probably bet on multiple things, and but I'm interested. I don't know how much this will have an impact, but the amount of the number of EVs is accelerating massively. And once all these EVs can participate in the grid, I think so. Octopus Energy in the UK now has, I think, 1.1, at least one. Last time I checked, it was 1.1 gigawatts. Out of our total maximum power is about 35 gigawatts. So 1.1 gigawatts of flexibility from plugged-in EVs alone. So that is a massive resource on the grid, as storage. From having these EVs. So that's only going to increase as a flexibility resource as more and more people get EVs on their drive.
Right. So they have like a 1.1 gigawatt BESS storage, right?
Yeah, but 1.1 gigawatts of not of storage themselves, but of additional flexibility from people's EVs.
Right.
So it's like storage, but a bit more unpredictable.
Right.
And
depending on the time of the day they charge and so on. Yeah. Okay.
So that's an interesting software application that I haven't talked about, but is cool.
Perhaps also going to the other questions, carbon nano yarn was looked a lot into for transmission during the late 2010s for transmission. Do you know if it has matured or is it still very researchy?
What was that? What did you say, Lena?
Carbon nano yarn. That was
interesting. I don't know about that example specifically, but I have heard of it. Kind of goes along with graphene and other kind of nanostructured carbon, that in principle they would make amazing conductors because they're 1D and you have very little resistance in these like carbon nanotubes and carbon nanoyarns. But I think there's still a challenge of actually producing them cheaply at scale with like a long enough yarn to reap the benefits of the low resistance in them.
So it's probably still researchy.
Yeah, although I have seen a couple of startups in that space, but only at a materials innovation level, not at a actual deployment into
product. Yeah. Okay, cool. How do you see the future integration of more compute at more places of the very analog as less advanced grid, e.g. advanced transformers versus traditional coils?
Sorry, can you repeat that?
Sorry, this was Jonathan questions. That's Jonathan ask, how do you see the future integration of more compute at more places of the very analog, less advanced grid? So I guess it's about the more compute, like the digital on an analog grid.
So I think
also, Jonathan, if you want to speak more about your question, also please really jump in.
Yeah, sure. Thanks so much, Chloe, for the great talk. I was in energy markets previously, so I have a keen interest. The question is essentially is the benefit of having more compute, say, to coordinate the grid activities and make better decisions at various places in the grid, including at these, for example, for advanced transformers that you mentioned, would be sort of have some form of compute or intelligence in them. I mean, probably not super advanced, but at least we can be more flexible and create better efficiency overall and less volatility. So I guess that's where I'm going.
Yeah,
that makes sense. Yeah.
I think that's in the short term. Like part of the benefit is just visibility of the grid. Like we have there's obviously many more smart meters, at least in the UK, and in other places now that give some visibility, but the data doesn't give that much. It gives a lot more information than there has been, but not that much about the power quality. So introducing these kind of solid state power electronics based transformers, gives that visibility and allows for more control. They're like surprisingly analog, the way they're controlled. You know, it's somebody calling up saying, oh, we need to fix this thing over here. The risk with these power electronics is that, you know, if there's a failure in the power electronics, that it could lead to failure of that distribution grid, you know, or outages. And in general, as with any innovations, they're super risk averse because their main priority is to keep the lights on. So the introduction of these more digital technologies, that's kind of the risk. But I think there's a lot of innovation happening, as I understand it, in terms of like mitigating the risk of that for power electronics, like better safety features and better kind of like backup features in those power electronics. One thing that Ionate have that is kind of their USP is that they have these hybrid intelligent sort of these hybrid transformers where if their power electronics fail, it kind of defaults to being a normal transformer again. So that's kind of a great way to manage the risk of introducing these new technologies, but also getting the capabilities of the advanced transformer as well. So I think it's like a risk of introducing these new software and the cybersecurity risks as well, but also, you know, like recognizing that the massive benefits that you get from it in efficiency, in control, in monitoring, and testing. And another thing that's a big problem, as I understand it, in introducing new technologies to the grid is what's called death by pilot. You know, they'll do loads of pilots with lots of different DSOs, these operators, and then never get deployed at scale. So I hope that's changing because it seems like there's such an appetite for these new technologies and people really recognize the benefits of them. But that has been, you know, a complaint in the past that they do loads of pilots, but they're actually too risk averse to implement any of these technologies. Yeah.
But this is actually I learned about this also during a recent conference. Like, and I was really like, it was for me really not understandable why this death to pilot where it comes from, because there was always so much money also poured into the pilots. Also, like, I mean, well, within the European Union, and then why basically it didn't transform into a long-term project. But a good hint there.
Yeah, it'd be interesting. I might try and learn more about that because I don't know the kind of diagnosis of that either.
Not limited to the energy sector. This happens elsewhere as well. Right? Thanks so much. Anyway.
Thank you.
Yeah, that's where you think the sunken costs would help. But then a question from Felix with regards to the topic: how does hardware versus pure software affect your investment hypothesis as an investor?
So
Felix, perhaps also if you want to jump in, if there is any further explanation, also feel free.
I'll give a quick answer, and then I'd love to hear your thoughts if you have them. So we tend to invest in mostly hardware, which I guess is quite unusual for a VC. We don't really invest in software, at least not pure software digital companies. And part of the reason for that is that we genuinely believe that to solve the climate crisis, you need to be investing in things that genuinely, like, you still need to make the cement. You need to make the cement without carbon. You need to like move all these atoms and molecules that use fossil fuels and actually need physical things to replace them. So that's why we focus on hardware. Now, because the grid is such a complex system, I think it's actually one of the most impactful areas for software to have an impact. And so it's kind of an area, I'm a chemist, I'm not software. I don't have experience with software. So it's kind of one of the areas where I wish I did, because I would love to invest in all the cool software technologies that you can have for the grid, like, you know, routing management, like there's like routing software where you can design, what is the best of a design for your project to get around permitting laws, but also the lowest cost and the shortest distance, or flexibility management to manage all these EVs as your distributed energy resources, or just like all these, so many really impactful software plays in the grid. But I'm less well informed to understand, to be able to compare which one is better than the other from a software perspective. But I'd love to hear your thoughts about what you think on this question.
Yeah, I'm thinking, I think, quite into the same direction. It's just a very general question, purposeful, but the question that I see is many investors love software, only software, so pure software. And I have the feeling that pure software doesn't solve the topics that you're tackling. So the question is, yeah, how does that, like, of course, hardware always comes with software together, but like to make it specific, if I understand you correct, you don't believe in pure software solutions, but only in combined hardware software solutions.
Yeah, it's not that we don't believe in them. I guess as an investor, you also need to have some focus for your kind of mission. And we just think that the hardware, in terms of climate impact, will have the biggest, in general have the biggest impact. And because you're genuinely fully transforming some of these industries, will also be a massive kind of financial opportunity as well.
Yeah, sure. But you as an investor are optimizing for financial return
Yeah.
with a specific hypothesis, but in the end, it must pay out financially, right? So
yeah. Climate decarbonization, and if these companies are big successes, they will have financial returns and have an impact as well.
great.
Yeah.
Thank you.
Yeah, perhaps also, is there any last question? Also looking at the time. Otherwise, I had one final one, which I always ask. What is for you and for that specific topic, kind of like the space that is most undervalued? Because often, I mean, a lot of investors run for the similar topics. It's like one topic is hot, but do you see any topic where actually not so many investors look at yet, but do you think this is actually like either they're on a technological level, we're close to basically seeing some breakthrough, or you already see really promising startups, you just haven't found the right one?
Do you think in the grid space or just in technology in every area?
You get both grid, but also your entire investment focus. Happy for both to open this up.
In my entire investment focus, I honestly think grid is a great area to invest, because we need so much more of it, and people are scared of this death by pilot, or investors are reticent to invest, but we're going to need many new technologies in this area. So I think in general, it's a great space to invest.
Okay. So basically overall grid is the undervalued topic.
I think
Okay,
so.
cool. Hopefully, after this talk, also a bit more VCs will look into it to give a boost to the entire industry. But yeah, thank you so much, also Chloe, for this really insightful talk, and also the great questions.